Okay. Well, sorry for that. Sorry for that. I hope you can hear me now. Yes, good morning. I hope you can hear me now. Hello. Good morning. Hello. Aha, they said they can hear me now, but they can't see my face. Okay. Sorry for that. This is Professor Ajayi, the coordinator of Chemistry 102. Sorry for that little challenge. I said I'm to take you through the chemistry. I'm to take you through the chemistry of I'm to take you through alcohol chemistry. Okay. And like I said, what do we mean by alcohols or alkanols? They are organic compounds in which hydrogen atom of an aliphatic carbon is replaced with a hydroxy group. That is, they are hydroxy compounds of the general formula ROH. The OH group is attached or bonded to the saturated carbon atom. That is, the OH is attached to carbon, which is an sp3 hybridized carbon atom. Alcohols as well can be thought of as organic derivatives of water, in which one of the water hydrogens is replaced by an organic group. Like I said here, you can see this water molecule here, okay? And you can see an alcohol. So you can see that one of the R of the water molecule has been, one of the hydrogen atom of the water molecule has been replaced by R, and R can be an alkyl group, okay? So the presence of OH makes alcohols polar and capable of hydrogen bonding. Of course, that also makes it very soluble in water. Okay, that makes it very soluble in water. Now let's quickly go to classification of alkanols. Alkanols are classified into three on the basis of the type of carbon atom to which the OH group is attached or bonded to. For a primary alcohol, you will see that the OH is attached to a carbon also carrying two hydrogen atoms, or the OH is attached to carbon that is attached to one other carbon directly. And therefore, for primary alcohols, the functional group is a CH2OH. And a quick example is ethanol, which is here. You can see the OH is attached to carbon having two hydrogen, and that carbon is also attached to just one other carbon. So that makes it a primary alcohol. Okay. Then the second classification, the second example is secondary alcohol. And secondary alcohol, the OH is attached to carbon that also carry either one hydrogen atom or two other carbon atoms. An example is this. This is an example, and this is two propanol. 2-propanol. The OH is attached to the second carbon carrying only one hydrogen, and it's also bonded to two carbon atoms. And the functional group of a secondary alcohol is this, as we see here. Then the third one is the tertiary alcohol. Okay, and the general formula is this, as we see here. The carbon to which the OH is attached to carries no hydrogen atom, but carries 3 other alkyl groups, and that makes it a tertiary alcohol. And an example is this one here, which is 2-methyl propantuol. 2-methyl propantuol is an example of tertiary alcohol. Now, alcohol can be further classified on the basis of the number of OH group per molecule or attached to different carbon atoms. An example is monohydric. The first example is monohydric alcohols, in which one OH is attached per molecule. One OH group is attached per molecule. And a quick example is also this example here is ethanol. Ethanol, you have only one OH. Now, for the second one, which is dihydric alcohol, it means dihydric means 2 hydroxy group. 2 hydroxy group is attached per molecule. An example is your ethane 1,2-diol. Ethane 1,2-diol. So ethane 1,2-diol or glycol, it's also commonly called glycol, is a dihydric alcohol because 2 OH group is attached to one molecule. The third one is a trihydric alcohol, in which 3 OH group is attached per molecule. And a very good example is glycerol. Your glycerol. Glycerol is propan 1,2,3-triol. Propan 1,2,3-triol. So that's an example of trihydric alcohol. And the fourth one, we call it polyols or polyhydric. Poly means many. So, and that can be 3 or more. In fact, anything more than 3, because already we have trihydric to mean 3 OH per molecule. Now, polyols or polyhydric alcohols, a very quick example is sorbitol. Sorbitol, you can see it here. Sorbitol has 6 OH groups. Okay, sorbitol has 6 OH groups. So it's a very good example of polyhydric or polyols. And another one is pentaerythritol. You can see it. This one has 4 OH. 4 OH, pentaerythritol. Okay. Now let's also look at other the IUPAC, the naming of alcohol. How do we name our various alcohols? You can see here, we can name by using IUPAC system, or we use the common classification, and I will take us through the two. Now, let's look at this one here. The OH, the parent alcohol is a butane. The parent alkane is butane. Now, the OH is attached to the first carbon atom. So that means this is carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4. And that means what the name is 1-butanol. 1-butanol, that's the IUPAC name, or butan 1-ol. And the common name for this is N-butyl alcohol. And if you look at it very well from our classification, you see that the OH is attached to carbon containing or carrying other 2 hydrogen atoms. That makes it a primary alcohol. So butan 1-ol or N-butyl alcohol is a primary, is classified as a primary alcohol. Another example, the second one here, you see, It's also the parent alkane is also butane, and the OH is attached to the second carbon. You can see the second carbon. Okay, that makes the carbon also bears one other hydrogen, and that makes it a secondary alcohol. A secondary alcohol. So the IUPAC name will be 2-butanol because the OH is attached to carbon 2. The OH is attached to carbon 2, and that means it is butan 2-ol or 2-butanol. And if you look at it closely, you will see that the carbon bearing the OH also carries one hydrogen atom, and it also carries two carbon atoms, and that makes it a secondary alcohol. A secondary alcohol. And the common name now, just like we have common name for butan 1-ol, which is N-butyl alcohol. This second one is sec-butyl alcohol. Sec-butyl alcohol, because sec means secondary. Okay, and let's look at the third one. The third one, you can see that the carbon here, the parent alkane is 1, 2, 3, 4. 1, 2, 3, and 4 here. Okay. 1, 2, 3, 4. You look at the longest chain. We are looking at the longest chain here. For the longest chain, it goes this way, not here, 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 no, but rather the longest chain here is 1, 2, 3, 4, and that makes it also a butane. Okay, and the carbon bearing the OH carries no other hydrogen, and that makes it a tertiary alcohol. A tertiary alcohol, but the carbon bearing the OH also carried a methyl group, and therefore the IUPAC name is 2-methyl. That is, on that carbon carrying the OH also carries methyl, so that means 2-methyl 2-butanol. 2-methyl 2-butanol, or 2-methyl butan 1-ol, whichever way you call it is correct. Okay, and it's a very good example of a tertiary alcohol. A tertiary alcohol. I'm leaving these two here as an assignment for you. Name it. Okay, name it yourself. I think I can give my first attendance code now. Let me give my first attendance now. I hope you are with me. Can I write it? Okay. So the first attendance code is capital Y, capital M, 5, capital M, and U. YM5MU. Okay. I hope that is taken. Thank you very much. So let's continue. So we continue. Now, let's now look at the rules or how to name an alcohol. The common name of an alcohol combines, let's first look at the common names first. So the common names of an alcohol combines the name of the alkyl group with the word alcohol. Okay, the other time, I said N-butyl alcohol. So that's a common name. So if the alkyl group is complex, then the common name becomes awkward, and the IUPAC name should be used instead. So common names often incorporate obsolete terms in the name of the alkyl group. For example, amyl is frequently used instead of pentyl for a 5-carbon chain. Okay, for a 5-carbon chain, that is pentyl, we can use amyl. Okay, so I think an example is this one. An example is this one that I gave you the other time. This 2-methyl 1,2-butanol. We can call it tertiary amyl alcohol because it has 5 carbon. 1, 2, 3, 4, 5. Okay, tertiary amyl alcohol. So let's go on. Let's also look at this. Okay, I think we've talked about this. So this one here, the IUPAC name is, you can see, carbon 1. You look at the longest chain, carbon 2 and carbon 3. So it is 2-methyl 2-propanol, 2-methyl 2-propanol, or 2-methyl propan 2-ol, 2-methyl propan 2-ol. And the common name can be tertiary butyl alcohol, tertiary butyl alcohol. And this other one here, okay, this is a cyclic, this is the parent name, the parent compound here, or the parent alkane here is a cyclic one. This is cyclohexane derivative. Now with the OH on position 1, it is cyclohexanol. It is known as cyclohexanol. That's the IUPAC name. Cyclohexanol, or if you like, cyclohexan 1-ol. Cyclohexan 1-ol. It can also be, the common name can also be cyclohexyl alcohol. Cyclohexyl alcohol. If you say that as common name is correct. But for IUPAC name, it is either cyclohexan 1-ol or cyclohexanol. Now let's look at this other one. This other one here, you can see that we have carbon 1, 2, and 3. And between carbon 2 and 3, there is a double bond. Okay, there is a double bond, and therefore still an example of alcohol. But this one we can call it an enol because it has double bond as well as OH. So 2 functional groups. So we call it enol. So the naming is like the other ones. The carbon bearing the OH is given number 1, the next carbon 2, and the last carbon here 3. So the name will be 2-propane 1-ol. 2-propane. It is 2-propane because the double bond is between carbon 2 and 3. It's between carbon 2 and 3, and therefore you give the carbon bearing the lowest number, the name. So that's why it is 2-propane 1-ol. And the common name can be allyl, because C double bond C is an allylic group. So it is allyl alcohol. Now the last one here, this one, the OH is attached to carbon carrying 2 hydrogen. So that's carbon 1, carbon 2, carbon 3, and carbon 4, because we are looking at the longest chain, carbon 4. So we have 1, 2, 3, and 4. And for this one, it is 3-methyl 1-butanol, or 3-methyl butan 1-ol. 3-methyl butan 1-ol, or 3-methyl 1-butanol. You are fine. Now for the common name, just like I told you, how many carbon do we have there? 5. And we said we use amyl here, okay, instead of pentyl for a 5-carbon chain. And since it has 5-carbon chain, 1, 2, 3, 4, 5, even though the 5th carbon is a substituent, it's a methyl substituent. It can also be called isoamyl alcohol, isoamyl alcohol. Now, using the IUPAC system, the name for an alcohol uses the OL suffix with the name of the parent alkane. You know, I've been talking about parent alkane, parent this since the beginning. Now, I want to now give us the rule guiding the naming of these alcohols. So I'm saying that using the IUPAC system, the name for an alcohol uses the OL suffix with the name of the parent alkane together with a number to give the location of the hydroxy group. The rules are summarized in 3-step procedure. So the first one here, you have to name the longest carbon chain that contains the carbon atom bearing the OH group. You have to do what? You have to name the longest carbon chain that contains the carbon atom bearing the OH group, and then drop the final E from the alkane name and add the suffix OL. For example, let's look at this example here. You can see this is carbon 1, carbon 2, carbon 3, carbon 4, 5, 6. Even though there are substituents on carbon 3, methyl substituent on carbon 3, and chloro substituent on carbon 2. So 6 carbon means the parent alkane will be what? Will be hexane. So the parent alkane is hexane, but on carbon 3, we have OH, and on carbon 2, there is a chlorine substituent. So the name will be 2-chloro, 3-methyl, 3-hexanol. So you remove the E of the hexane and put OL. So it now becomes 2-chloro, 3-methyl, hexane 3-ol. So you can say it is 2-chloro, 3-methyl, hexane 3-ol, or 2-chloro, 3-methyl, 3-hexanol. You are correct. Okay. Now the next one. Let's look at the second rule. It said number the longest carbon chain starting at the end nearest the OH group and use the appropriate number, if necessary, to indicate the position of the OH group. See, in the first example I gave, if you go from this anti-clockwise way, okay, no, this is clockwise rather. So you can see this is carbon 1, 2, 3, 4, 5, 6. But if you want to go anti-clockwise, it will be 1, 2, 3, 4. So the carbon bearing the OH will be 4. So we can't go through that route. Rather, we must go through the clockwise route that gives the smallest number to carbon bearing the OH. So we go through this 1, 2, 3, 4, 5, 6. So that becomes 2-chloro, 3-methyl, 3-hexanol, or 2-chloro, 3-methyl, hexane 3-ol. Now let's look at the second example. This is a cyclic alkane, parent alkane bearing OH. And if you look at it, since this is an alcohol, we start numbering from the carbon bearing the OH for this one. So 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. And that means we have 2 diameter, because the carbon 2 of this cyclopentane carries carbon 2 carries 2 substituents, 2 methyl substituents on the same carbon, and therefore it is 2,2-dimethyl cyclopentanol. Okay. Third rule says name the substituent and give their numbers as for an alkane or alkane. We've done that already. So let's move to Okay. Now let's look at the physical properties of alcohols. Physical properties of alcohols. Okay. No complaint. I hope there is no complaint. We saw, yeah, no, you don't need to submit. You don't need to submit the assignment. You don't need to submit. Just do it. Keep it. Okay. Yes, OH is given priority, of course, because we are treating alcohol. So OH is given priority. Okay. Yes, the U is capital letter in the attendance code. The U is capital. Check. I've given you the attendance code correctly. So just check this chart. You will see it there. They are all in capital letter. Okay. All right. So let's go back. Now we are on physical properties of alcohols. Already I've talked about two of them. I said one, they form hydrogen bonding, and two, that they are soluble in water. Now, let's go through others. Now, I said most of the common alcohols, they are colorless liquids at room temperature. Methyl alcohol, that is methanol, ethyl alcohol, that is ethanol, then isopropyl alcohol are free-flowing liquids with fruity odors. And the higher alcohols, that is those containing 4 to 10 carbon atoms, are somewhat viscous. I can tell you that. Butanol is an example. N-butanol is somehow viscous, and butanol has 4 carbons. So as you go up from carbon 4, they are viscous liquids. They are viscous liquid, or we can say they are oily, okay, and they have heavier fruity odors. So some of the highly branched alcohols and many alcohols containing more than 12 carbon atoms, they are solids at room temperature. So please get that trend. The first three carbon, that is alcohol with 1, 2, 3 carbons in a straight chain, they are liquids at room temperature. They are liquids and they have fruity odors. And I say also that the higher alcohols, that is those containing 4 to 10 carbon atoms, that they are viscous. They are viscous liquids, or you can say oily liquids, and they have heavier fruity odors. Okay, and I said some the highly branched alcohols and many other alcohols containing more than 12 carbon atoms. Those ones are solids at room temperature. They are solids at room temperature. So please get that. Okay. Now the boiling point of alcohols. Let's look at the boiling point of alcohols under the physical properties. Alcohols generally have higher boiling points in comparison to the other hydrocarbons having equal molecular mass. For example, butan 1-or has a higher boiling point than butane, which is the alkane counterpart. That is, they all contain 4 carbons. So alcohols generally have higher boiling point in comparison to other hydrocarbons having equal molecular masses. And this is due to what? The presence of intermolecular hydrogen bonding. Intermolecular hydrogen bonding, R OH, R O H can bond with oxygen of, so you can see this is intermolecular hydrogen bonding, that is between alcohol and water. Okay, so if you put alcohol in water, also you between themselves ROH and form hydrogen bonding with oxygen of another alcohol. So you can see, okay. Now, I said this is due to the presence of intermolecular hydrogen bonding, which can be either intra or inter, which is the bonding between hydroxy group of the alcohol molecules, like I showed here. This is one alcohol molecule, this is another one alcohol molecule, and you can see the hydrogen bonding between the hydrogen atom of one of the alcohol and the oxygen of another alcohol. So in general, the boiling point of alcohols increases with an increase in the number of carbon atoms in the aliphatic carbon chain. Okay, and on the other hand, the boiling point decreases with an increase in branching in aliphatic carbon chains, and this may be and that the van der Waals forces also decreases with a decrease in surface area. Get that, please. Get all this underlined, in your notes. Get this underlined. Okay. Thus, primary alcohols have generally a higher boiling point. Now, let's look at what causes. Let's look at this hydrogen bonding of a thing. Now, the oxygen atom of the strongly polarized OH bond of an alcohol pulls electron density, like I'm showing here, pulls electron density away from the hydrogen atom. This polarized hydrogen, which bears a partial positive charge, as you can see, can form a hydrogen bond with a pair of non-bonding electrons on another oxygen atom. Oxygen has two lone pairs. I'm sure you know that. Two lone pairs, which it uses easily to form hydrogen bonding with a hydrogen atom. So this polarized hydrogen, which bears a partial positive charge, this carries a delta negative, and this one carries a delta positive charge. Okay, and this can form the hydrogen bond with a pair of non-bonding electrons on another atom. Okay. Another thing that I mentioned under the physical property of alcohol is solubility. Solubility of alcohols. The solubility of alcohols in water is governed by the hydroxy group present. So there is this interconnectivity between hydrogen bonding and hydrogen bonding, then boiling point, and solubility. All depend on this factor, which is hydrogen bonding. So the solubility of alcohol in water is governed by the hydroxy group present. The hydroxy group in alcohol is involved in the formation of intermolecular hydrogen bonding. Thus, hydrogen bonds are formed between water and alcohol molecules. I said it the other time. Look at it. This is alcohol forming a bond with hydrogen of water. So you can see the hydrogen bonding, and this makes alcohol very soluble in water. I said thus, hydrogen bonds are formed between water and alcohol molecules, which make alcohol soluble in water. However, the alkyl group attached to the hydroxy group is hydrophobic in nature. Okay, and thus the solubility of alcohols decreases with the increase in the size of the alkyl group. Okay, the moment this alkyl group is increasing, then the solubility of alcohol reduces in water. So I say, however, the alkyl group attached to the hydroxy group is hydrophobic in nature. Thus, the solubility of alcohol decreases with the increase in the size of the alkyl group. Alcohols with higher molecular weights tend to be less water soluble. For example, let me give us an example. CH3OH we will be more soluble in water than CH3, that is butanol, CH2, 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 OH, that is methanol, will be more soluble in water than butanol due to the increase in the length of the alkyl group. You can see the alkyl group, 4 carbons, and methanol is just 1 carbon. Okay, so alcohols with higher molecular weight tend to be less soluble, water soluble, because the hydrocarbon part of the molecule, which is hydrophobic. Hydrophobic means water hating. When you say hydrophobic or hydrophilic means water loving, philic means loving, and phobic means hating. So the alkyl group is hydrophobic, that is water hating, while the larger it is, which means increase in molecular weight as well, it means that alcohol will be less soluble in water. Now, because they are strongly polar, alcohols are better solvents than hydrocarbons for ionic compounds and other polar substances. Now, we are now looking at some special properties. Should we call these physical properties? I think we are more going into chemical properties now. So can we call this slide? Can you name it the chemical properties? The chemical properties of alcohols. Now, let's look at the acidity of alcohols. Okay, I think I can give the second attendance code now. We have done about 40 minutes. Okay. So I'm typing it, so just pick it from there. L, B, K, all in upper cases, Z, and W. L, B, K, Z is B. L, B, K, Z, W. So that's the second attendance code. And it's already posted on the chat menu. Now, we are looking at the acidity of alcohols. Let's look at the acidity of alcohols. Alcohols react with active metals such as sodium, potassium, etc. to form the corresponding alkoxide. Just like we have hydroxide, we also have alkoxide. Okay? Now, these reactions of alcohols indicate their acidic nature. Just like even water. Water also have its kind of, yes, we say it's neutral, but we'll see very soon. So the acidic nature of alcohols is due to the polarity of the OH bond. So the acidity of alcohols decreases when an electron donating group is attached to the hydroxy group, as it increases the electron density on the oxygen atom. Thus, primary alcohols are more acidic than secondary and tertiary alcohols. What are we saying? CH3OH is more acidic than CH3, CH2OH. Okay, we are saying that that is one. Primary alcohols are more acidic, okay, or this is a primary, you can say this is primary alcohol and this is also primary, but the more the carbon, the less the acidity, because we said this here, we said the acidity of alcohol decreases when an electron donating group is attached to the hydroxy group as it increases the density on the oxygen atom. So, and we now say generally, primary alcohols are more acidic than secondary. So this one here is more acidic. The two of them are more acidic than CH3, CHOH, CH3, that is 2-propanol or propan 2-ol. These two are more acidic than propan 2-ol. However, methanol is more acidic than ethanol. Okay. Number two, let's look at the formation of our alkoxide. You know, a sodium, for example, sodium metal will react with water to give sodium hydroxide and liberate hydrogen. Is that not so? Okay. The same thing we have here, acidity of alcohols in the formation of alkoxide. If sodium forms a hydroxide with water, also sodium or metals also form alkoxide with alcohols. So alcohols are weak acids. Alcohols are weak acid, and the most acidic simple alcohols, which are methanol and ethanol, are about as acidic as water. And most other alcohols are less acidic. They are less acidic. And you can, let's see here. We say a strong base can deprotonate an alcohol to yield an alkoxide ion, that is Ro minus, just like we have HO minus. For example, sodamide, which is sodium NH2, that is NaNH2, is a very strong base, and it abstracts the hydrogen atom of an alcohol. So metallic sodium or potassium is often used to form alkoxide by reducing the proton to hydrogen gas in an alcohol. So you can see ROH reacting with sodamide, and it's giving us a strong alkoxide here. Okay, this is an alcohol reacting with sodamide, or an alcohol reacting with sodium metal, okay, which is, that sodium metal is a reducing agent. Okay, so reacting, you have sodium alkoxide. Also here you have sodium alkoxide, and in the sodamide, ammonia is liberated, but with sodium metal, hydrogen gas is liberated. Okay, that shows a kind of relative acidity of alcohols in the formation of alkoxide. Now, let's look at preparation of alcohols. Preparation of alcohols. The various we have looked at the physical and the chemical properties of alcohols. Now, let's look at their preparation. How can we prepare them, both in the lab or otherwise? Number one, by catalytic reaction of carbon monoxide with hydrogen gas under high temperature and pressure. Okay, and here, if you carry out this reaction, that is a catalytic reaction of carbon monoxide with hydrogen gas under temperature and pressure, that is a temperature of about 300 to 400 degrees Celsius, under 200 to 300 atmospheric pressure, and a catalyst. You can see carbon monoxide, that is 1 mole of carbon monoxide plus 2 mole of hydrogen gas, which we call synthesis gas. With the catalyst and that condition, methanol is formed. This is a simple way of forming of preparing methanol. This is for methanol preparation. Okay, another method with which we can prepare or that is commonly used to prepare an alcohol is by hydration of alkenes. Hydration of alkenes. Now, hydration means addition of water, of course. So the addition of water across the double bond of an alkene will yield an alcohol. That is, you are adding water across the double bond of an alkene, of course. So, the water will be this. So you are adding this to one carbon and you are adding hydrogen to another carbon. So the simplest way across the double bond, across the double bond, across the double bond. Okay, so in most cases, water adds in the direction that places the new hydroxy group on the more highly substituted end of the double bond. This is according to the Markovnikov rule. I hope you still remember Markovnikov rule. Professor Olomola took you through Markovnikov, in his classes. So we don't need to say much. I don't need to say much on that. Okay. I said water is added in the direction that places the OH group on the more highly substituted end of the double bond, according to the Markovnikov rule, as an acid catalyzed hydration. So the more highly substituted end of the double bond is the one that is bonded to more carbon atoms. Now you can see here, this is propane, 3 carbons, 1, 2, 3. Okay, 1, 2, 3. That is carbon 1 and 2. There is a double bond across carbon 1 and 2. Now, adding, that means carbon 2 is the more substituted. Carbon 2 is the one that is more substituted, and therefore you can see the OH is on the carbon 2. So this is carbon 1, this is carbon 2, and this is carbon 3 here. So carbon 2 is the highly substituted. So the OH from water is added. Of course, in the presence, the hydration is done. That is, addition of water is done in the presence of H2SO4, okay, which is acting as a catalyst there. Okay, so you can see the OH is attached to carbon 2, okay, to carbon 2, while the hydrogen is attached to carbon 1, and therefore we now have 2-propanol. So propane is hydrated to form 2-propanol, and what we have here is a Markovnikov orientation. That is, it obeys the Markovnikov rule there. Now, for the second one, let's look at the second one. The second one, this is 1-methyl cyclohexene. 1-methyl cyclohexene. So here, for this cyclohexene, this is carbon 1, and the one down is carbon 2. This is 3 and 4 and 5 and 6. Now, hydration of this, the OH goes to the highly, of course, I'm sure you know that there is another hydrogen here on carbon 1. There is another, okay, we have 1, 2, 3, okay, 4. So the double bond will give away, and OH is added to the same carbon 1, which is the highly substituted carbon. So, and now we have 1-methyl cyclohexanol. 1-methyl cyclohexanol. Next, by fermentation. So we can produce alcohol by fermentation method. Okay, and this is the one easily done by the locals in the preparation of what we call ogogoro, and that is ethanol. Okay, they carry out this through what we call fermentation. And what is fermentation? Ethanol or ethyl alcohol that is produced since prehistoric times, mostly through the fermentation of fruit juices. So you can ferment fruit juices or some seeds, some carbohydrates. Also, some people even they use cassava. You can produce alcohol from cassava. You can produce ethanol from maize, and so on and so forth. I mean, from starchy foods. So many different sources can provide the sugars and starches that are broken down to simpler compounds during fermentation. So ethanol is called grain alcohol. Ethanol is called grain alcohol because it is often made from grains. You know, I said that, such as corn, maize, wheat, rye, and barley. So the grain is first boiled in water to produce the mash, which is incubated with malt, sprouted barley. Malt is a sprouted barley, that is barley that has been that is sown, that's just sprouting up. It contains malt, okay, and that will yield the wort. So malt provide the enzyme which is called diastase that converts starches in the grain to sugar maltose. Okay, so the wort is incubated with brewer's yeast, which secretes the enzyme maltase to convert maltose to glucose. You do a lot of this in food chemistry with Professor Otemuyiwa, which will come the last part of this lecture. Professor Otemuyiwa will come and will take you through this. Now, can I quickly, before I finish this class, can I quickly give us the okay, let me give the third and the last code. The last code, which is F9 E J and Y. F9 E J and Y. Okay, that's the last code for today. So as we round up, that means I will round up alcohol tomorrow, but let's see where we can stop today. Now, I said Professor Otemuyiwa will take you through food chemistry. We talked about carbohydrates. Under carbohydrates, you look at disaccharide, monosaccharide, polysaccharide, and so on and so forth. Proteins, fat, and oil. So under that, you do more of this conversion. I mean, of this maltose, which is a disaccharide. Now, 2 of the 6 carbon atoms. Okay, sorry, I said the wort is incubated with brewer's yeast, okay, which secretes the enzyme maltase, which converts maltose to glucose. And the enzyme zymase also converts glucose to ethanol. So we have 2 of them there. Okay, the 2 of the 6 carbon atoms in glucose, they are oxidized to carbon dioxide, and this oxidation provides the energy to the yeast. And then you have the equation for the conversion of maltose to glucose. Okay, maltose is a disaccharide. You hydrolyze it with water in the presence of maltase, you get 2 units of glucose. Okay, now the glucose is now in the presence of zymase, which is another enzyme which converts the glucose to ethanol, carbon dioxide, and energy, 26 kilo energy. I mean, kilocalories. Now, let's now look more on the chemical properties of an alcohol. Apart from acidity of alcohols that we have done, and also its reaction with metals, we still have other chemical properties which we are going to look at today and tomorrow. And one of them is oxidation. Alcohols undergo oxidation in the presence of an oxidizing agent to produce aldehydes, ketone, and ketone, which upon further oxidation give carboxylic acid. For example, look at this primary alcohol. You oxidize it, and of course, I think you understand the elementary definition of oxidation. It means addition of oxygen or removal of hydrogen. So it is either you add oxygen to this, okay, or you remove two hydrogen. It's either you add oxygen or you remove two hydrogen. Okay, so for a primary alcohol, if you oxidize it, it will give you aldehyde. Okay, if you oxidize it further, okay, it will give you a carboxylic acid. To give you a carboxylic acid. Okay, but if you have a secondary alcohol, if you oxidize that, then you obtain a ketone. So an aldehyde, oxidation of primary alcohol will give aldehyde. Why? If you oxidize secondary alcohol, you get a ketone. So we'll continue from here tomorrow. So let me give chance to the next class. Okay, so we'll meet tomorrow. All right. Kí ló ń ṣẹlẹ̀? Ẹ bẹ̀rẹ̀. Ẹ fẹ́ kó jẹ́ ìwọ́n tún fi bẹ̀rẹ̀ ra ń tù.
Come. Okay. No, still.
Okay.
I was.
Okay. Thank you. Because okay.
Can I start now?
Good morning, class.
Yeah, we met since last Friday, and how was your weekend?
Yes. Today, by the grace of God, we will continue from where we stopped. Don't forget, we were able to consider those homes. We were able to do the those materials that actually obey Ohm's law and those that do not obey Ohm's law, and that was where we solved some problems. So we want to look at series resistors, when resistors are connected in series. Yeah, thank you for all this. So let's move on from that. Now we want to consider having, let's just assume we have three resistors, R1, R2, R3 connected in series. The first thing that you need to know is that the same current that is flowing through R1 will also flow through R2, will flow through R3. But their potential difference, the PD across each, depends on the resistor. Take, for example, V1 depends on R1. V2 depends on R2. V3 depends on R3. And that was what. So the total PD, if I now have a bigger, like the one I have for the battery now, so the total PD will just be V1. V is equal to V1 plus V2 plus V3. And that is what I mean by the total potential difference is the sum of the individual. You sum the individual potential, and that is where you have that V1, V2, V3. So the individual potential is directly proportional to individual resistance. You know, I mentioned, I've said that. I said the PD V1 depend on R1. The V2 depend on R2. And that is what you can see here. And what we are saying is your V1 will be equal to R1, the same current that is flowing, times R1. I times R1. V2 will be I times R2. Likewise, V3 will be I times R2. You can see that I is the current, the same current flow. As I've mentioned in the diagram, you can see the same current flow through R1, R2, R3. And that is why R is constant. And then if you substitute that expression, that V1 equals IR1, V2 equals IR2, V3 equals IR3. If you substitute in the above equation, V is equal to V1 plus V2 plus V3, you are going to have what we have in equation 10. Because I will cancel, and that is this. When you talk of resistance in series, the effective, or what you can call equivalent resistance, or the resistors of the resistance of the resistor, we just give you as the sum of the individual resistor. So you just have R is equal to R1 plus R2 plus R3. Please, this is no more chemistry 102. This is physics 102. Physics 102. So let's continue. I believe you can see my slide. So you should be able to see the slide. Yeah. Okay. So don't forget, we have mentioned about series. So we are talking about parallel now, because I'm very sure you are familiar with this. In your secondary school, you are familiar. So we don't need to emphasize, spend the whole day in doing it. So if you have three resistors, it can be more than three, but we are just using three. Just let's assume that there are three resistors connected in parallel. R1, R2, the same R3, just like what you are. But you can see the arrangement. This is parallel, not like the previous one that we said is series. So you can see that the total current that is flowing in the circuit will not be the same, just like what we did for the first one. When we are talking in terms of parallel circuits, what determine, you can see that the current I1,
depends on the value of R1. The current I2 depends on the value of R2. The current I3 depends on the value of R3. So you can say that the total current will just be the sum of the three, I1 plus I2 plus I3. That is what you will have. And if you do that correctly, you can see that equation 11. What we have in equation. Can we get the slide? You will get it. Don't worry. I've asked the secretary of the course. He's going to send it to you. But you can see. You can still see on your this thing. Don't worry. You will have it. You will have it. By the grace of God, by the end of this week, I should finish with my. Maybe we have class on Friday. So by Friday, I think I should finish with my own area. And if I'm not able to finish, then we finish on Monday. And I'm sure by Monday, you will have the slide. So no problem. Don't worry. You will have the slide. So the total potential difference, that is where we are going. You can see in the series, we said the same current flow. But in this case, it is the same PD across all. So if you are having R1, R2, R3 in parallel, the total PD will just be the same. It will be equal to V1. V is equal to V1, is equal to V2, is equal to V3. But don't forget, we said I is equal to the sum. You sum it. I1 plus I2 plus I3. So if you combine all those parameters, don't forget V1 will just be equal to V, will be equal to V2, will be equal to V3. But you will have your V1 to be equal to I1 R1, V2 I2 R2, V3 I3 R3. So if you put the value, make I the subject. If you make I the subject, then you can now have, you will have V all over R, V all over R, V all over R. That is V all over V1 all over R1, V2 all over R2, for V3 all over R3. That is for I1, I2, I3 respectively. So if you substitute in equation 11, don't forget we said our V1 is equal to V2 is equal to V3 is equal to V. V is the effective, or you can say combined potential difference, or the voltage across the circuit. So by the time you substitute that value, you find out that the effective resistance, the reciprocal of the effective resistance, is equal to the sum of individual, very good, the PD across it, each is the same for parallel circuit. So you can see the effective one will just be 1 all over R is equal to 1 all over R1 plus 1 all over R2 plus 1 all over R3. And that is how we got equation 12. Our equation 12. Very, very important. So don't forget, we mentioned some things when we were talking about Ohm's law, that your I or your PD is proportional to I, where R is constant, and we said R is the nature, is the material. You talk about the nature of the material. And we also mentioned something important. We said it unless, the law is obeyed when all the physical properties are constant. Do you get it now? Physical property. And one of the physical property that we want to talk about is temperature, which means as temperature changes, definitely it will affect your resistance, the resistance of the wire, of a given wire. And that is why I've given you, this is the relationship. Do you know, we got this from the expansions of solid. If you can remember, if you can say the coefficient of expansion is equal to increase in length all over original length and change in temperature. The same thing is applied here. If you want to know the resistivity of a material that is temperature independent, then the total or the effective resistivity will just be equal to rho, that is resistivity of 0 plus bracket 1 plus, don't forget, that is the coefficient of expansion times the temperature difference. T minus T naught. Initial, you have your final. So the difference is what determines your resistivity. So resistivity at a temperature T, where you have your rho whole 0 is the resistivity at some reference temperature T naught, and your alpha is the temperature coefficient of resistivity. So if you do that, you will have this proportion. And that is how your equation 4 and 14 is obtained. Like what I've just said, coefficient of expansion. Thank you. I mean, I know some of you are very serious. You said it's a secondary school work. So thank you very much. So you can see from here now that if you now relate it, don't forget there is relationship between resistivity and resistance. So if you now bring it down to resistance, in terms of where you see resistivity replaced with resistance. So the same thing, resistance at temperature T is same thing as resistance at temperature T naught, 1 plus alpha, coefficient of expansion, times change in temperature, equation 15. So these are very important. Yes, we need also to talk about what we call electromotive force. You know it. When you have a circuit, you have your battery. You know, as I used to use this to explain. As you are standing or you are sitting down, you are picking your pen, you are walking, you are doing, there is something in you, part of your energy, that is, you have energy in you that is helping you to pick your hand right. That is not, we may say that in physics, that is not work done, but you need energy to drive your cell. The same thing when you have your battery, because of the material that is made up of, there is ability of that cell not to produce the 100% that it's supposed to produce. Why? Because of what we call internal resistance of that particular cell. So the PD across a cell you can use it to determine the internal resistance of, take for example, if the PD is 1.5 volts, and you are getting, by the time you connect your external voltmeter, and you are getting 0.05, you can see that what we are saying is part of 0.45 has been used to drive energy through the cell, because the total is 1.5. Then by the time you connect your voltmeter, you are getting 1.05. So it means 0.045 has been used to drive current through the cell. That is, the cell itself used part of it. So, and that is what brought about what we call the internal resistance. So the internal resistance is determined once you are able to, if I want to know if I'm able to get the PD across the cell by connecting, and I have your resistance, then external resistance, if I vary this and I'm measuring this, I can determine the internal resistance. And that is what will lead us to the equation that we have, equation 16. The total EMF will be equal to, if you look at this, your total EMF will be just equal to PD across your R. Your PD is PD across your R, which is the same thing as V, plus PD across your internal resistance R. So which means where you have that dash line, you can still connect a potential difference, a voltmeter, to measure the PD across it. And when you have that, then the sum, that is PD across small r plus PD across big R, will give us the total potential difference, which we call your electromotive force. And that is how we got this. So if you can remember equation 17 now, look at equation 17. You know, I told you, I give you an example. I said, assuming you have a battery and the voltage, the electromotive force of that battery is 1.5. That is the total, the capacity of that battery. But by the time you connect your external circuit, you discover that it's measuring 1.05, which means 0.45 is used to drive current through it. And that is where you are having IR will now read 0.45. If my E is 1.5 and my V is equal to 1.05. And that is how we got this equation. You can see from here, your E is equal to, look at what I wrote here. Don't forget, it's just simple mathematics, and that's why you are having it here. So you can make your, take for example, if I want I can just say I is equal to E all over R plus small r. Yeah, yes. It means you are having that. So if you are now having, you can get your I in terms of, please don't forget, for you to get I mean the equation that you are having under the equation 16 is just straightforward. From, if you have, take for example from here, I can rearrange. I can bring E, I mean R bigger R is equal to big E minus IR. So by the time you simplify, you can multiply. From here now, you can multiply, and then you get your I is equal to ER all over big R plus small r. That is very, very important. So, and then you can have that your equation 17. Look at what I said. I said equation 17 give the terminal potential difference when the battery, that is with electromotive force, maintain the current. If the current that is flowing is that current I. Suppose, however, that a current is passed through a battery in opposite direction. Can you see now? In opposition to the EMF as shown in below. So if you have, you can see now. This is what we mean by as shown below. That is in the opposite direction. The figure showing a generator Y sending a current I through a battery X in the opposite direction to the EMF. The net potential difference will just be VAB minus E across the terminals. Maintain the current I in R. Then you have A is equal to, can you see? This is where you're having EAB, that is the electromotive force across this, which you have here, will now give us exactly E, that is that of this battery divided by, plus IR. And that is why the equation below is very important. So you can see now, it is very important for us to know, definitely, as I said, as you are, for you to be able to say that I want to work today is because you have the ability to do work. Is that not true? So which means there is something that is driving, you are using part of the energy by yourself. You don't know, but it's the energy that, your blood is flowing. So part of the energy is used by your body itself. So you will not get 100% of the total energy that you have. So for you to get the total energy, and that is what brought about this work done. And we are saying that the electrical work required to transfer a charge, the same thing apply, required to transfer a charge through a potential difference of this. So the potential, if I now want to calculate the work, it will be charge times the voltage, where Q is charge is measured in coulomb and V measured in PD. Then the unit will be, the unit of this will now be joule. That is how you will determine the electrical energy. That is how the electrical energy is determined. And don't forget, we said the electrical power delivered by an energy. So please, for the attendant code, I want you to write it now. 6, I can write it there. Okay, thank you. 6, write it. 6 C J M F. That is the first one. C. That is the attendant code for the faculty. For the first one, write it down. I will give you the second one in the next 5 minutes. Then the third one when we finish. So just as I've said, the unit is joule. Yes, that is the attendant code. Write it down. I mean, what I mean is you know how to do it. So I won't teach you that. I'm sure you know. So you can calculate the power. Don't forget, power you said is work done per unit time. So you can get your electric power. So, and that is how we got electrical energy or work divided by the time. And that is where you have it. Don't forget, when we started, we said Q all over T is your current. And that is how we now obtain our current. Can you see? Q all over T is I. So if you multiply, you have that. So you can see that power is IV, which is given by, you can begin to change, assuming your V is not given. V is equal to IR. If you substitute, you have I squared R. Then if your I is not given, assuming it's current that is not given, I know that current is V over R. So substitute in the equation IV, you will have V squared all over R. And that is how you get it. Don't forget, because you are dividing by time, the unit of power is joule per unit, joule per seconds, and we call it watts. So that's why 1 watt is equal to 1 joule per second. So, and from there, you can calculate your energy. Energy, since from there, power times time will give you energy. Don't forget. But that notwithstanding, we can get our energy to be equal to Q times E, where E is what you can call the total electric, thank you very much, total EMF. That is how we get it. Please, it's total EMF. This is E. This E that you are having is not V. I will have used V, but I know you will be confusing it. That's why I use capital E, EMF. So from there, since you know that is Q, you know Q is IT. That is from the beginning when we started. IT, that is current times time, will give us that. So by the time you simplify, you can see that this is the same thing as IET, which we always write as IVT. It's still the same thing, but be careful when we are talking about the energy, work done, electrical work done, then is IET, and then you can get that and you relate to that. So you can calculate the efficiency of your generator. Take for example of the one that is generating. I call it generator because it's the one that is generating your electric current. So for me to calculate, you find the ratio of the power output all over power input. That is times 100%. That will give you the efficiency. So you can just substitute in, and then you can see power output all over power generated. So power input all over power output. I mean power output all over power input. That will give up. You can now see how this power is coming in. We know the power IV all over I. So if you multiply very well, you just don't forget, because of E that we are saying, you substituted it. So for me to get the efficiency of the power, I can still find the ratio of resistance. But because this is E, if you look at what we have here, power output all over power input. Can you see? Power out all over. Power output is your V, and power input is your total EMF. So from here, I can relate. If you have look at what you can see that this will be, I will cancel. Then you have R all over R plus small r, and that is why. So if I know the ratio of the resistance, I can substitute to get your efficiency. So please, the second code, I want you to write the second code. GX, okay, let me write it. GX 7 NE. That's the second code. GX7NE. So that is the second code. So you can now put it in. So from here, we need to move on. You can, as you have gotten your, you can see, this is just manipulations. You can just, to get your IR, and just substitute. And don't forget, I said, since I is equal to this, you got it from here. Substitute this one in your power output. That is how we are having E squared R all over R plus R squared. One of them is saying that there is no need to sending the code. Why is there no need? Okay, I don't want to. It's not my. It's okay. So the next one is when you have your, you can arrange your battery. If, take for example, I need a battery of 24 volts, and what I have at home, I have two battery of 12 volts. What will I do? I have to arrange them. The best way to arrange is to arrange them in series, so that I will have 12 volts plus 12 volts to make 24. If I need, let's assume that I need 36 and I have 12 volts. What I will do is I will add all the three in series. I will combine them in series, and that's the example we have here. E1 plus E2 plus E3. If they are connected in series, is the sum. You need I've given you an example. You need a battery of 36 volts, but at home you only have three of 12 volts. So what you do is you connect them in series, and that's what we have done. So for series connection, I'm going to have E total PD, or the total electromotive force, will be E1 plus E2 plus E3. Are we getting me? Then, since the batteries are connected in series, it implies that the internal resistance will also be connected in series. And don't forget, when we were talking about arrangement of resistance in series, R is equal to R1 plus R2 plus R3. So for this one too, I will just have small r1, small r, the effective internal resistance will be small r equals to small r1 plus small r2 plus small r3. That is, if you are not having so many battery, take for example, those of you that have inverter that is connecting, you have to connect your battery in series. You have up to 100 that you are having. You want to generate a very high voltage, so you need to connect them in series. So you will connect, your total here will just be E1 plus E2 plus E3 plus E until you get to EN, the last one. So, and the internal resistance will also be like that, because each of the battery is having their internal resistance. So you have the effective internal resistance will be small r1 plus small r2 plus small r3 until you get to your Rn. For parallel, take for example, I want my battery to last long. I need 12 volts. If I need 12 volts, I can still connect 3 battery. And I will tell you the reason why it's going to last long. I can still connect 3 battery. I need 12 volts. And I have 3 battery at home. And I don't want to let all the 3 live value. I don't want to connect one. I want my battery to work effectively. So what will I do? Because it's 12 volts I need, and I have 12 volts each for each of the battery, I will connect them in parallel. Are you getting me? So if you connect them in parallel, the total voltage will still be E, will just be 1. It will still be 12 volts that you'll be reading if you connect in parallel. But look at internal resistance. The internal resistance will help you to reduce the work done. Look at what we have. Because you connected them in parallel, their internal resistance, each of them will have internal resistance, but internal resistance are connected in parallel too. So from what we learned about in parallel connection, what will you do? 1 all over r small r is equal to 1 all over r small 1 plus 1 all over r small 2 plus 1 all over r small 3. And by the time you sum up this, you discover that your internal resistance will be very small. It will have been reduced. So which means it's just like a person that is very healthy. is given a small work to do, within a very short time, what will happen? You will finish it. So your battery, your system that is using 12 volts will not be your battery will not be overpowered. It will just be working steadily, and it will last long because you have reduced the internal resistance. Because by the time you find the reciprocal, you discover that the internal resistance of that battery will be very low. The internal resistance of that battery will be very low. So you can now, I've given you so many, and I don't want us to just continue like that. Let me give you an example. You know, that's the way I work, and I've told you I want some of you that used to come to benefit. That's why I don't put my, what do you call it? I don't put my work example on slide, because I know all of you, those who are attending class and those who do not, we also have the slide. So I will only give you, or I will dictate to you. So I want you to write this question down now. Write this question down. I have some. I'm going to give you some, and I will give you some assignment. I will also give you the one you are going to do at home. Just one. Write it down. One, a 20 kilo ohms resistor is connected in series with a resistance of 40 ohms. A 20 kilo ohms resistor is connected in series with a resistance of 40 kilo ohms. Full stop. What resistance R, capital R, must be connected in parallel with the combination so that the equivalent resistance is equal to 20 kilo ohms? Let me dictate the question again. A 20 kilo ohm resistor is connected in series with a resistance of 40 ohms. 40 kilo ohms. Full stop. What resistance, capital R, must be connected in parallel with the combination so that the equivalent resistance is equal to 20 kilo ohms? I think for that one, you don't have problem. Don't forget, you are told, yes, a 20 kilo ohms resistor. Somebody have helped us to type it. That's good. That's good. A 20 kilo ohms resistor is connected in series with a resistance of 40 kilo ohms. Yes. Full stop. What is the resistance R? I mean, what resistance R must be connected in parallel with the combination so that the equivalent resistance is 20 kilo ohms. Please, it's not 20 ohms, it's 20 kilo ohms. Thank you very much. To do that, very straightforward. First of all, you have been told, yes, 20 kilo ohms. Yeah. Thank you very much. So you have been told that two are connected in series. Those that are connected in series, I can just say, okay, let my R, because it's not effective it's effective that I'm looking for. But the one that connected in series, let me just say R1 is equal to R 20 kilo ohms plus R 40 kilo ohms, because they are in series. You had them. So if you had them, what will you have? You are having 60 kilo ohms. So you are now having 60 kilo ohms connected in parallel with your R. Can you see now? 60 kilo ohms connected in parallel with your R to give 20 kilo ohms. So very simple. So for the parallel, we have done it. We've mentioned it. 1 all over R equivalent will be equal to 1 all over R1 plus 1 all over R2. Now you can now say, okay, my R2 will now be R. My R1 will just be 60. Oh, somebody, very good, you have done it. The person Adeboye Victor, is it Victor? Victor Adejare, yes, 30 kilo ohms. The answer is 30 kilo ohms. Yes, he's the one that got it. We just say 1/20. Don't forget, 1/20 is the effective one. So you just say 1/20 is equal to 1/60 plus 1/R. So make it the subject. By the time you do that, you just get your 30. It's 30 kilo ohms, not 20. 30 kilo ohms. Yes, it's 30 kilo ohms. Another one, another question. Write this one down. Or maybe I can give you the third code. The third code. Yes, the third code is C, capital C, E, D, A, X. That's the next one. The next, the last code. So you just put that last code. So the next question, a current of 2 milliampere, a current of 2 milliampere flows in a radio resistor R, capital R. When a PD, that is when a potential difference of 4 volts is connected, what are the value of the resistance and the conductance? What is the value of resistance and the conductance? Please, I have given you conductivity, and we related conductivity to resistivity. So conductance will be related to resistance. So 1 all over resistance will give us conductance. That's what I just want you to know. But that notwithstanding, you can do it. The first one, how do we calculate the resistance value? Very easy. You know, as I've said, yes, a current of 2 milliampere flows in a radio resistor R, capital R. When the PD of 4 volts is connected, what is the value of the resistance and the conductance? Very good. That's the question. So you get your R. Don't forget, your R is for the external circuit. If you do it correctly, your R will be 2 kilo ohms. How will you get that? Small r is equal to V all over I. And I know if you look at that equation, your V is already there. You know the PD, it has been 4 volts. You know your I is 2 milliampere. Just divide them. So you find your R will just be equal to what? 2,000 ohms. And that's what I called 2 kilo ohms. 2 kilo ohms. Then your conductance, as I've said, is just 1 all over R, because we are talking about conductivity. I gave you the definition of conductivity. So 1 all over R. So if you do that one correctly, it will be 5 times 10 raised to minus 4. Yes. We call the unit Siemen. S-E-I-E-M-E-N. Even, German equipment used to carry this, is the conductance. Yes. Just capital S, capital X, capital S like this. That's the unit. This is the unit of Siemen. Yeah. So that is how we can get that. Let me give you this one, and then you do it yourself. I'm not going to do it for you. Your take home. A battery of EMF 1.5 volts has a terminal PD of 1.25 volts. When a resistor of 25 ohm is joined to it, A battery of EMF 1.5 volts has a terminal PD of 1.25 volts when a resistor of 25 ohm is connected or is joined to it. Full stop. Calculate the current flowing. Calculate the current flowing, comma, the internal resistance small r. Second question, calculate the current flowing, comma, the internal resistance small r and the terminal PD when a resistor of 10 ohms is replaced by 25. Can you see now? You now replace 25 resistor. So I want how many answer? 1, 2, and 3. I want 3 answer from you. If you do it correctly, the first one, the current is what? If you do it, I want you to do it at home. If you do it correctly, the answer will be 0.05 ampere. 0.05. 2, the internal resistance. If you do the internal resistance very well, it will be 5 ohms. And the last one, if you calculate the PD, the terminal PD correctly, is 1 volt. See you on Friday. Yeah. See you on Friday. Thank you very much. Mo ní class mi ní 10. So